Hi everyone, today we're going to talk about single slit diffraction. Now before we get into single slit diffraction, we're going to talk a little bit about double slit interference, which was the topic of last class. So in double slit diffraction, we were starting with 2-point sources exiting two slits that were very closely spaced. Those 2-point sources provided us with some nice monochromatic, which means one single wavelength, coherent light that interfered just like any other wave would, producing an interference pattern on a screen a certain distance away. This produced regions of bright and dark spots. In last class, we described some equations that describe the spacing of the interference pattern depending on which light or dark fringe you were interested in looking at. Now, in the early 1800s, Young, who performed this experiment initially, established the relationship between the distance between the slits, the wavelength of light, and the distance to the screen, and the distance between bright or dark bands. He was actually able then to calculate the wavelength for different colors of light. Visible light is, of course, made up of different colors, each of which has a different wavelength. And the wavelengths are in the range 400 to 750 nanometers. Here's a diagram that shows the generally accepted ranges for each of those wavelengths. Notice how there's no purple light? That's not actually a wavelength. So at this point in history, things were looking pretty good for describing light as a wave. However, someone pointed out, and this someone was Simon Poisson, that if light were a wave, if we pass light past a circle, some sort of obstacle, a bright spot should be detectable in the middle of the shadow of that circle. Now, that's due to the interference of light around the sharp edges of that circular object. And guess what? With the correct technology, they were actually able to detect this bright central spot in the shadow of a circle. This is actually usually referred to as a Poisson spot, a Fresnel spot, or an Arago spot, depending on who you want to attribute this phenomena to. Notice also in this picture, which is a simulation, that there is an interference pattern that exists around the outside of the circular shadow as well. This interference pattern will actually happen around any sharp-edged object. If you want to see this pattern clearly, you're going to need monochromatic light to see it clearly, and that light should be coherent. Now on to single slit diffraction. We're just looking at light as it passes through one single, very, very tiny opening. So when we pass light through a single slit, if the width of that slit is comparable to the wavelength, and we're talking hundreds of nanometers or tenths of micrometers here, we are going to observe a slightly different pattern when projected on a screen a certain distance away. Diffraction of a wave is something that we've talked about in class before, probably last year. So let's take a quick look at a simulation, the ripple tank simulation, to see and remember what diffraction actually is. In the past, we talked about diffraction, which is the spreading out of a wave past an obstacle. Here you can see a point source, and the waves are actually spreading out or diffracting around this obstacle. In our case, we're interested in what happens when a wave passes through a single slit. Notice what happens in this case. If I were to put a screen over here, you would see a number of interesting features. You would see a very bright region in the center, which is what we're going to observe. You would see a region right here of destructive interference, followed by a less intense region of constructive interference, followed by a region of destructive interference, and that pattern would be repeated on the other side as well. Now, one way to visualize this in our attempt to explain what's happening is to recall Huygens' principle. As a wavefront approaches and reaches a single slit, we're going to consider every single point along the wavefront as a source for a secondary wavelet. This is going to allow us to imagine the propagation of this wave. Not only is it going to allow us to visualize what's actually happening as that wave propagates, but it's going to let us describe each of those waves as a ray as well. If we draw rays emanating from all of these primary and secondary wavelets. So it is useful to draw light as a ray even when we're doing this sort of analysis. So in this diagram, we have primary and secondary wavelets. So we're imagining an infinite number of little tiny wavelets existing along this tiny little single slit, producing more wavelets, resulting in the diffraction of this wave, which is light. In this scenario, there are a couple of variables to define. We have the width of our slit, W, which again is very, very small. And then we have a certain distance L away, some sort of screen where we're going to capture this interference pattern. On this screen, eventually, we're going to want to measure the distance from light to light or dark to dark bands, but we'll do that a little bit later. The other important thing to remember is that in all of these diagrams, the scale is exaggerated. So the length from our single slit to our screen is huge compared to this tiny little distance W where the light can actually pass through. Now, the first thing we're going to look at is the bright spot in the center. In this example, we've got a whole bunch of different rays, which we're representing as passing through our single slit. Because this single slit is so small, all of these rays are going to be effectively parallel all the time. However, a very, very long distance away, comparatively speaking, they're all going to hit the screen at the same point. So these rays are traveling the same distance. They're all going to act constructively when they hit the screen. So what that will result in, once it hits the screen, is a very, very bright central band in our diffraction pattern. Now we're going to think about what happens when these waves interfere destructively when they hit the screen. Now, in order to visualize this, for all of the examples that follow, we're going to divide up our single slit into a bunch of separate rays. We're going to pair up these rays and ask ourselves, under what conditions would each of these little pairs of rays interfere destructively once they reach our screen? If they interfere destructively once they reach our screen, we'll get a dark spot. There will be no intensity of light hitting the screen at that point. So let's take a look at our first example. We're going to look at the first region where destructive interference occurs. That's our first dark band right beside our central bright band on the diffraction pattern. So in this example, we have a whole bunch of little light rays we're going to imagine coming from our single slit. They're color-coded because we're going to pair them up in a second. Let's start by taking a look at these red light rays here, which are currently spreading out from our single slit due to diffraction at an angle θ1 to the horizontal. Now, these two light rays are actually going to travel a different path length. The difference in their path length is going to be half a wavelength if they're interfering destructively. Now, the same thing can be said with each of these other pairs of colored rays that we've drawn. We're going to get to that in a second. First of all, let's just look at this red pair of rays. Here's this triangle, which is sketched out at the bottom of the diagram here. The height of the triangle is just the width of the slit divided by 2. The difference in path length required for destructive interference is lambda over 2, and the angle we're interested in this case, we're going to call θ1 because it's our first dark band. So we can say, using a little bit of trigonometry, sine of θ1 is equal to opposite side, lambda over 2, over hypotenuse, w over 2, which just gives us the relationship lambda over w. So, when sine θ1 is equal to the wavelength of our wave divided by the width of our slit, the red rays, which are color-coded in our diagram, will tend to act destructively. So this ray will always cancel this ray. No intensity once it hits our screen. Now let's look at the blue rays. Those two blue rays are going to experience the same pattern. At θ1, their difference in path length will be lambda over 2. Therefore, they will interact destructively as well, producing no intensity at the screen. Same thing if we look at this pair of orange light rays. These orange light rays have a path difference of lambda over 2, therefore they will interact destructively as well. Same thing with this other arbitrary pair that we've drawn in this diagram. They will also interact destructively. It doesn't matter how many pairs we draw in our diagram, maybe an infinite number of pairs of rays, all of them will act destructively. Therefore, no light will reach the screen at θ1. What does this tell us? For the first dark band, we can rearrange the formula we came up with here, and we can say the wavelength, if we wanted to do a little bit of measuring, let's say we measure θ1, the wavelength is just equal to w times sine θ1. θ1 is just the angle where our first dark band occurs. Now let's do the same thing, but let's look at the second region of destructive interference, which we will say occurs at an angle θ2 to the horizontal. In this case, we're going to do the same thing. We're going to divide up our slit into a whole bunch of different rays. We're going to pair them up and figure out what needs to happen for each pair of rays to interfere destructively once it hits our screen. This time we're going to divide it into 4. And now you can see, if we're just looking at our red color coding, these rays can interfere destructively among the bottom 2 pairs. And then the upper 2 pairs will also interfere destructively. We're going to end up constructing the same little triangle because we're interested in knowing when is the difference in path length equal to half a wavelength. Here's what those triangles look like for our bottom pair of red rays and for our top pair of red rays. So in order for a dark spot to appear on the screen now, each pair of rays has to have a path difference of lambda over 2. Using a little bit of trigonometry, this means sine θ2, which is opposite over hypotenuse, is just 2 lambda over w. That's our new relationship. Same thing goes for every other colored pair of light rays in the diagram. So this green colored ray will interfere destructively with this green colored ray, producing no light at our screen. Same thing for this green ray and this green ray. So we can pair up every single ray in the diagram and see that they all interfere destructively in pairs. Therefore, the second dark band, if we measure θ2 where this occurs, we can say 2 lambda equals w sine of θ2. Noticing a pattern yet? If we divide the slit into 6 equal pieces next time and pair up our light rays, we can also figure out what relationship needs to occur for all of those pairs to interfere destructively, again producing complete destructive interference once they hit our screen. You probably guessed the pattern already. This one is just sine θ3 equals 3 lambda over w, using the same method that we used before. So in general, for the nth dark band, which is a minimum, n lambda equals w sine of θn. In this case, n starts at 1. We're going to start with our first dark band, n equals 1. Second dark band, n equals 2. Third dark band, n equals 3, and so on. One note to be careful with. We're starting to come up with equations that look very similar for the equations we used for double slit interference. So just be careful about A, what these equations look like, and B, how they're numbered, because it can be a little bit different. For double slit maxima, the relationship we came up with last time was sine θn equals n lambda over d. N began counting at 0 in that example. In this example, single slit diffraction, and in this case, we're just looking at the minima. Sine θn equals n lambda over w looks very similar, except this time n starts at 1. So just keep that in mind. It's a good idea to make a summary sheet for yourself so that you can make sense of these different equations. Now let's look for the maxima. When do the maxima occur, and how does that work for a single slit diffraction pattern? Of course, the first maxima is our brightest, and that's right at the center, when theta equals 0, and the light rays are traveling purely horizontally. But as the light rays diffract when they go through the single slit, we will get regions of constructive interference, just not as bright, and we're going to figure out why that is. We're going to do the same thing we did before. We're going to take our single slit and we're going to imagine a whole bunch of light rays are going through it. In this case, we're going to divide up our single slit into 3 chunks. And we're going to pair up light rays and figure out what condition must be met for each pair of light rays to interfere destructively. So let's take a look. We'll again start by pairing up these randomly color-coded light rays. So we'll start with the pair at the bottom that are red. These 2 red light rays will interfere destructively when the difference in their path length is again lambda over 2. So this will give us 3 lambda over 2 equals w sine θ1. But now let's look at our diagram. This top light ray doesn't have one that will interfere destructively with any other light ray. Therefore, it's going to make it to the screen without interfering destructively. However, when it makes it to the screen, it's going to produce a bright spot that is much dimmer than our central bright spot, which is exactly what we notice. Now, if we perform a similar process with all of the other light rays in that diagram, we're going to find the same thing. Light rays from the bottom 2/3 of that slit are going to interfere destructively with each other when their path length is different by lambda over 2. However, the top third of light rays from that slit will not interfere destructively. They will make it to the screen, producing a bright band. Not as bright as the central band, though. So for the first order maxima, we can say 3 over 2 lambda equals W sine theta 1, where theta 1 now refers to the angle where the maxima, the first order maxima, occurs. For the second order maxima, we're going to do a similar analysis. This time we're going to divide that slit into 5 equal pieces. We're going to pair up light rays that will interfere destructively, and we're going to figure out that only the top fifth of the slit is going to produce light rays that actually make it to the screen without being canceled out, without destructively interfering with another light ray. Therefore, this will happen when 5 over 2 lambda equals W sine theta 2. We can continue dividing the slit up into smaller and smaller pieces, and we're going to find that as we're looking at higher order maxima, the amount of light coming from that slit that actually makes it to the screen is smaller and smaller, meaning the intensity of light that we see in the diffraction pattern gets dimmer and dimmer as we're looking further from the central peak. So in general, for the nth order maximum, which does not include the central band, we can say n plus a half lambda equals W sine of theta n. Or, another way of rearranging that equation, sine theta n equals n plus a half lambda over W. In this case, again, n is equal to 1, 2, 3, 4, 5, so n starts at 1. Again, be careful, do not confuse this with the equation for minima in a double slit. It does look similar, however, it is distinctly different. So make a summary sheet for yourself, make sure all of these things are in order. Here's a nice diagram summarizing what we found so far. Notice how our central bright band is twice as wide as any other bright band. We call that the central zero order maxima. That's the brightest maxima that we have in a single slit diffraction pattern. For the dark bands, the first order maxima is the first dark band after our central maxima. The second order minima is the second dark band. The third order minima is the third dark band. And we've just come up with relationships so that we can figure out what angle this occurs for. Same thing for the maxima. Our first order maxima is the first bright band past our central bright band. The second order maxima is the second bright band past our central band, and so on. Now onto an example. Let's calculate the angle at which 7.5 times 10 to the 2, so 750 nanometer light, produces a secondary minimum if the single slit width is 0.2 millimeters. So we have a couple of things that are given. We're given the wavelength of light. We're also given the width of our single slit. And we want to figure out what is the second order minima, which we actually just summarized right here. That's our second order minima equation. This is why it's so important to summarize these equations for yourself so you can find them really quickly. So summarizing what we're given, n equals 2, we're talking about a minima, so we're talking about a dark band. We've got the wavelength, we've got W. Now we just need to plug into this equation. Plugging in, we get an angle of 0.43 degrees. Pretty tiny angle. Next example. Monochromatic light falls onto a slit 2 times 10 to the minus 5 meters wide. The angle between the two first order dark fringes on either side of the central maximum is 4 degrees. Calculate the wavelength of light. So in this case, I'm going to use a diagram we used a couple slides ago to make sense of what they're describing. They're saying the angle from the first order minimum here to the first order minimum here is 4 degrees, meaning theta 1, which is the angle between our central peak, the center of our diffraction pattern, all the way to n equals 1 for our minima, our first order minima, is just 2 degrees. And we're talking again about a dark band. So we use that same equation. Sine theta 1 equals lambda over W. Plugging in, and we can actually figure out the wavelength of light. The wavelength of light is 698 nanometers, which happens to be red light. Now, whenever we're looking at a diffraction or an interference pattern, it's so much easier to just measure the spacing of the bright and dark bands on our screen rather than measuring the angle. So let's replace theta, or theta n, with x, or xn, the separation or distance from the center of our diffraction pattern to any of the light and dark bands. So on this diagram, instead of writing theta n, we're now going to write all of the distances in terms of x. So for maxima, we're always going to measure from the very central part of our diffraction pattern up to the center of our bright band. So x1 would be the center of our first order maxima. x2 would be the center of our second order maxima. And that goes for the top or bottom of our diffraction pattern. For minima, we're measuring the same idea. So we're measuring from the center of our diffraction pattern up to the center of our first dark band, x1, center of our diffraction pattern up to the center of our second dark band, x2, and so on and so on. Now, when we were doing this for double slit interference, we made a simplification. L is much, much, much larger than the width of the slit. Therefore, xn, this distance here, over L, which is equal to tan theta, is approximately the same as sine theta, because we're talking about really, really, really tiny angles since L is so much larger than xn in this case. Using that relationship, using that assumption, which is a good assumption in this case, we can actually come up with a relationship very similar to the ones we've come up with before to describe the various maxima and various minima in terms of the distances on our actual screen when we're looking at an interference pattern from a single slit. Keep in mind, this is similar but not the same as the relationships you found for a double slit. So be careful not to get these confused. Next example, a helium neon laser, which has a wavelength of 632.8 nanometers, passes through a 43 micrometer slit and creates a diffraction pattern on a screen 3 meters away. How far is the third dark band from the middle of the central maximum? So in this case, the question is asking for x3 for a minimum. We've got the width of our slit, we've got the wavelength of light, we've got the distance between the single slit and the screen, and we want to figure out what is x equals 3 for a minimum. Using the equation from the last page and plugging in some numbers, we can figure this out pretty easily. It happens to be 13.2 centimeters. Here's a summary of everything we've just said. So for any minima, xn equals n lambda L over W, which means for the first order minimum, x1 is lambda L over W. Second order minimum, x2 equals 2 lambda L over W. Third order minimum, x3 is 3 lambda L over W. These are all distances, remember, that we're going to measure directly on the screen where we've projected our single slit diffraction pattern. As for maxima, the pattern looks a little bit different. Our first order maximum, not including the central maximum, x1 is 3 lambda L over 2W. x2 is 5 lambda L over 2W. x3 is 7 lambda L over 2W. If you want to think of this as an image, you can take a look at this image summary as well. Here's an example of the intensity of light as projected on a screen a certain distance away. Notice how the central bright band is much more intense than all of the other bright bands and twice the width. The first minimum occurs at lambda L over W. The second minimum, or dark band, occurs at 2 lambda L over W, and so on and so on. If we wanted to look at the bright spots, now we just have a slightly different pattern to follow in terms of our equations. Notice that the spacing from bright band to bright band is consistent with the spacing from dark band to dark band. That's going to come in handy in a second. So if we take a look at our pattern again, the first order minimum occurs at lambda L over W on either side of the center of our diffraction pattern, which means the width of our central bright band is just 2 lambda L over W. However, if we look from dark band to dark band, or we look from light band to light band, the spacing is consistent, and the spacing is just equal to lambda L over W. So we can also say delta X, the distance between successive dark bands or successive light bands, is equal to L lambda over W. This often gets rearranged in terms of the wavelength, since when we're looking at single slit diffraction, it's much, much easier to just measure things that are on the screen or distances that we've set up in our lab. Next example. A beam of green light is diffracted by a slit with a width of 0.550 millimeters. The diffraction pattern forms on a wall 2.06 meters beyond the slit. The distance between the two second-order minima is 8.2 millimeters. Calculate the wavelength of the laser light. So we're going to start with a little bit of a diagram. It's saying, what is the distance between the two second-order minima? Well, if we look at our diffraction pattern, here's our first order minima, here's our second order minima. So the distance between the second order minima, they're telling us, is 8.20 millimeters. We're also given the width of the slit and the distance to the screen. Now that we know that, we can solve this problem two different ways, which are equally valid. We could say, well, if this distance is 8.2 millimeters, then I guess x2, the distance from the center of my pattern to my second order minima, is just 4.10 millimeters. I know the equation for x2. I know it's equal to 4.1 millimeters, so I could just sub it in. Or I could say, let's look at delta x's. There are 4 delta x's between the 8.2 millimeters that were given in this question. So you could say 4 delta x is equal to 8.2 millimeters. We know the equation for delta x, therefore either way, it's a matter of plugging in numbers and solving. The answer ends up being 547 nanometers. Finally, the single slit result actually helps us better understand what we observe in reality when we look at a double slit interference pattern. In an ideal situation, when we have 2 point sources that are interfering to create a double slit interference pattern, we should be able to see light band, dark band, light band, dark band, all with equal intensity. However, that's not actually what's seen, because I want you to keep in mind, every single one of those double slits is also a single slit. So every single one of those double slits is producing a single slit diffraction pattern as well. So whenever we're looking at a double slit experiment, we actually see a combination of a double slit interference pattern and single slit diffraction pattern overlapped. So this, in combination with this, is what we actually see. Here's what that actually looks like as a waveform. Notice how the double slit interference pattern with regular bright and dark bands is enveloped in our single slit diffraction pattern. What this looks like on a screen is this. Here's our single slit diffraction pattern, our double wide bright central band, and then we have equally spaced but less intense brighter bands and darker bands petering off to the side. A double slit pattern actually looks like this. So we have bright, dark, double slit interference enveloped inside our single slit interference pattern.